My name is Jax Morrow, and this is my Chemistry 120 final project. So with this project, we're just going to look at the various metrics by which acids and bases can be defined, and then at the end, I'm going to give a brief demonstration using a few real-world analogies for these definitions. The first classification we're going to look at are Arrhenius acids and bases. This definition was created in 1884 by Swedish chemist Svante Arrhenius. An Arrhenius acid is a substance that increases hydrogen ion concentration when added to water, which, based off of some thermodynamics principles, it's not like a realistic thing. So what that actually does is increase the hydronium concentration in water. And an Arrhenius base is a substance that increases hydroxide ion concentration when added to water. And if you couldn't tell based off those definitions, this Arrhenius classification is limited in its application as that it only applies to species in aqueous solution. So roughly 50 years later, there were two other chemists who each independently came up with this classification that has come to be known as the Bronsted-Lowry acid-base definition. And what it states is that an acid is a substance that donates a proton, or a hydrogen ion, and a base is the substance that accepts a proton. The picture of the two of them are on the left, as well as a diagram of what this kind of acid-base reaction actually looks like. The final classification for acids and bases is the Lewis classification, and it was defined in 1932 by a chemist by the name of G.N. Lewis, and it states that an acid is a species that can accept a pair of electrons, while a base is a species which can donate a pair of electrons. And the Lewis salt/adduct is the molecule that is formed as a result of the reaction between a Lewis acid and a Lewis base. This is illustrated in the graphic on the right. It does involve hybrid orbitals, though, so it is more nuanced than the other two classifications. Now I am going to provide a brief demonstration that uses a few real-world analogies to help illustrate each of these definitions. Okay, now we are in the demonstration section of the video, and so what I'm going to do now is use a couple real-world analogies to help illustrate the differences in these various definitions. So the Arrhenius definition states that an acid is a substance that, when introduced to water, increases the hydronium concentration, and a base, according to Arrhenius, is a substance that increases the hydroxide concentration after it has been introduced to water. So what I have here is a blue bath ball. When I put this into my little bowl of water, the water is going to start turning blue. And so this would be analogous to, imagine I had an experiment set up and I was checking to see if a substance was an Arrhenius acid. So I have an indicator in my water that will turn blue if the hydronium concentration has increased to a significant degree. So if I put this in, after I introduce it to water, and I see this indicator, I know that the hydronium concentration has went up. So let's sort of see how that works. Yep, definitely dissolving. So in a lab setting under this analogy, this would be an Arrhenius acid. For the Bronsted-Lowry definition of an acid, that is something that donates a proton, and a Bronsted-Lowry base is something that accepts a proton. So using these little Lego pieces here, imagine that this little green block is a proton, and so this one has a proton that it can donate, so it's going to sort of pull that off and then donate it to the other piece. And so this initial thing would be my Bronsted-Lowry acid, and this would have been my Bronsted-Lowry base. But now that this sort of proton transfer has taken place, now I have my conjugate base and my conjugate acid. It's important to note that with the Bronsted-Lowry definition, this proton is transferred. It's not being borrowed by the base. It goes all the way through. Under the Lewis definition, a Lewis acid is something that can accept an electron pair, while a Lewis base is something that can donate an electron pair. So this would sort of be analogous to, if you can imagine, puzzle pieces. Obviously my Lewis acid has this concavity here that can be filled by this Lewis base, sort of just like that. And so really what this would be an unhybridized orbital, and this has electrons that it can share, and together they form this Lewis salt or Lewis adduct. But unlike with the Bronsted-Lowry definition, if this Lewis salt dissociates, my original Lewis base will keep the electron pair. It will not be fully donated to this Lewis acid.